This is your section 2 notes, frequency distributions. So a frequency distribution is basically a way to take your data set and group it together. Alright, so this is your book definition. Partitioning among several categories, we call them classes, by listing all of the categories along with the number of data values that fall in each of those categories or these classes. So for instance, let's say this is a data set, pulse rates. So in a minute, people were asked to calculate their pulse rates. This data set was made. This data set was made for the males. We're going to stick with the females. And if we group them into classes, 60 to 69 beats per minute, 70 to 79 beats per minute, etc. These are the numbers that fell in there. So just so you can see it, where these numbers are coming from are from the last data set. Oops. If I look at the numbers in the 60s, there's a 60, something in the 60s. So these are all the numbers that fall in the 60 range. And if I count up how many that is, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and that's where this 12 is coming from on the next screen. Okay, so that's what we mean by the frequency. It's just how many numbers in the data set fall in this range. And if you go back through and count, this is what the numbers look like for all of that. Okay, for all the different ranges. Alright, now breaking down this left hand side, the classes. So you'll see that we have everything has like a name. So the class limits are the upper and lower values on here. So lower class limits are the lower numbers, upper class limits are the upper numbers. Alright, and then class boundaries. The way we come up with a class boundary is we go in between these first two classes. So this one ends at a 69, this one starts at a 70. Right in between those two, if I took 69 and I added 70 to it and divided by 2, I'd get the number right in the middle, which is 69.5. Okay, so that's where this is coming from. 69.5 is the boundary between these two classes. So if I take that same approach all the way across, meaning that there's a boundary between these two of 69.5. There's a boundary between these two then of 79.5, etc., 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 89.5. If you keep that pattern going, we get these values. But notice the first one we computed, just to show you where it came from, was the average of these two, the boundary between the first class and the second class. But that doesn't account for all of this class. So what we actually do is keep this pattern that we see that we've created going all the way back one more notch on the pattern. So we go down to 59.5, and these would be the class boundaries for these classes. Alright, meaning all of these values, anything in the 60 to 69 range falls in between these two numbers. Anything between the 70 to 79 range falls in between these two numbers. Okay, so that's what we mean by class boundaries. Alright, class midpoints are exactly what they sound like. So if I took a 60 and a 69 and I divided that by 2, I'd get 64.5. Alright, that's the class midpoint for here. Alright, for this class. 64.5. And then same thing, if I add 70 and 79 and divide that by 2, I'd get 74.5. Alright, and then all the way down, I'd get that same thing. I get this for all the midpoints. Alright, 70 plus 79 divided by 2 is 74.5. This plus this divided by 2 is this. Okay, all the way down. We're just averaging these class limits. Alright, and then class width. Several ways you can get class width. The easiest way is to take your lower limit and subtract. So lower limit minus lower limit is 10. Upper limit minus upper limit is also 10, so you could also subtract the upper limits. You can also subtract the class midpoints, one from one from the other, or class boundaries. Okay, so all of those tell us that the class width is 10. All right, another thing to do when if it's discrete data like pulse rate is how many times you count a pulse in a minute. So it's a discrete data set because there's gaps between possible values. But another way, what it actually is that you're doing here is it's how many values can we take on in each class. And if you count, I can have 60, 61, 62, 63, all the way up to 69 here. And if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values, that can be in each class. Okay, so several different ways to count it, obviously, but that's the actual idea of what's going on. How many values can you take on within each class? Or, just the easy way to compute it, just the differences between the limits. Alright, what's the best way to come up with what your classes are going to be, or how we're going to construct our frequency distribution? So, determine how many classes that we want. Alright, you don't want really any more, any less than 5 classes. And this says 20, but I would really never want to see really much more than 10 or even 12 at the most. But our book says 5 and 20. Definitely no less than 5, but really no need for more than 12 usually. But if you see here, for this example we've been using this frequency distribution, we've got 1, 2, 3, 4, 5, 6, 7 classes. So I'm going to let that be 7. Okay. Now calculate the class width, the maximum value minus the minimum value. If we go all the way back to our data set, and these are the female pulse rates is the data set we've been using. The maximum was 124. The minimum was one of these 60s. There's a few of them, but one of the 60s. So if we come back down to here, we got a 124 for the max and a 60 for the minimum divided by 7. Alright, bring out my calculator. 124, make sure you do it in parentheses if you're going to do it all in one step. 124 minus 60 divided by 7 is 9.1. Okay, but because it says round up, even though that doesn't, but by rounding rules, round to 10, we would still round it up to 10. So that's going to be my class width. Okay, using this formula. Alright, now starting point, use your minimum value of the data set or a convenient value below that. That's what they did here. So they could have started at 60 because that's the smallest value of the data set, but they could also start at 60 just because of the convenience starting with a 0 as the last digit. So for instance, if the smallest value in the data set hypothetically had been 62, it would have still been fine to go down to 60. That's what this is saying, that convenient value. Alright, you just want to make sure that your lowest class contains the smallest value, basically. Alright, and then you just create your classes based on where that starting point is. Okay, and then you just go all the way until your last class is created, and your last class, however many classes that you picked in step 1, your last class should contain that maximum value if everything works out right, and especially if you do start with the smallest number. if you do that adjustment to move back to create a convenient number, you could have to possibly add an additional class, but it's not a huge deal usually. Alright, and then relative frequency is just frequency divided by the total. Alright, the sum of all frequencies, you'll hear me refer to that as total a lot of times. So any particular class divided by the total gives a relative frequency. And then, to change to a percent, this will be a decimal. Change to a percent, you just multiply by 100. That's equivalent of moving the decimal 2 places. So this is what they're showing us here is they take this 12, the total frequency is 40. We take 12 divided by 40, we get 0.3, and then 0.3 is the same thing as 30%. Alright, 14 divided by 40, 0.35, changed it to a percent, we get 35%. Okay, that's what they've done all the way down through here. Cumulative frequency. Think about how snow accumulates. Alright, so there's a little dusting of snow. It's snowing. Alright, over time, as the time goes on, the snow accumulates. Alright, so that's what we mean. Cumulative, think accumulation. It's growing, it's getting bigger, it's building on top of itself. So when we say cumulative frequency, so this class is the only thing that's less than 70. So there's only one class that's less than 70, so we have 12. But then if we go less than 80, here's 80. Both of these classes are less than 80, so we're adding 12 and 14, and we're getting to 26. All right, all three of these classes are less than 90, so we take that 26, add this next 11, and we get 37. And all the way down through here, we're taking this class, and then we're adding the next class to it to get the next number on the cumulative frequency scale. Okay, it's accumulating, it's building on itself. Alright, and then cumulative relative frequency, same thing. We start off with this as our initial percentage. Alright, but then we're accumulating relative frequency. Alright, 65 plus 27.5 is 92.5%. And then adding 2.5% to that would be 95%. Alright, adding nothing to that still keeps us at 95%. And then adding the last 2.5%. Oops, I got off one. 30, 65, 92.5, 95. Oops, yeah, I should be at 97.5. Alright, then adding nothing to that still keeps me at 97.5. Alright, and then finally adding the last one should get me to 100. Okay, and if you think about it, if this is the percentage breakdown of this, when you get to the very last number, this should always be 100. The only exception would be just because of rounding, and it still theoretically should be 100. It's because you rounded instead of keeping fractions is the only reason that this thing would ever be anything other than 100. Because 100 relative frequency, cumulative relative frequency, this bottom row, it's what percent of the data is smaller than a number bigger than your largest value. Well, everything's bigger than your largest value, or something bigger than your largest value. Alright, and then something we're going to move towards, the normal distribution. We call it the bell curve. You'll hear me refer to it as that as much as you'll hear me refer to it as a normal distribution. But the frequencies start low, then increase to one or two high frequencies, then decrease to a low frequency. So starts low, increases to a high frequencies, and then it goes back down to low frequencies. Alright, so that's what it kind of looks like. And if I connected the ends and put a little thing right there, it'd look like a bell, and that's where it gets its name, the bell curve. Alright, excuse me. And the distribution is approximately symmetric, meaning that a bell curve, if you cut it in half, it could fold over on top of itself. It's like a mirror image. Alright, so that's the very first section of chapter 2. If you have any questions about it, just send me an email.